All right, so now I'm going to summarize some of the things we discussed in this course on applied and computational topology. So the first thing it's like we talked about was really sort of what it means to say that something is topologically equivalent. And in order to do that, one needed to introduce the idea of topological spaces. So we discussed topological spaces. And it's like, and this notion of open sets, and that it's like a map is continuous if the pre-image of open sets are open, things along those lines. And that was essential because that allowed you to define what it meant for maps to be continuous. So this is sort of the most general space. Where sort of one can talk about sort of maps being continuous. And of course, this is important because that allows us to talk about this idea of homeomorphisms. Right? This leads to the notion of homeomorphisms. Right, which are basically so two spaces, two topological spaces are homeomorphic if there is a map that's like which is continuous from one space to the other, and the inverse is also continuous. Okay, and that's the notion of equivalence. It's like one is concerned with. It's like when one studies topology. Okay, so there's a map from one space to another. And both the map and its inverse right is continuous. All right, and then so this leads to the study of topology is about sort of properties of spaces that are invariant under homeomorphisms. So these are sort of typically it's like referred to as topological invariants, right? Okay. All right. So after that, it's like we started talking about curves. So we discussed sort of curves. And in particular, we looked at things like the Jordan curve theorem, and the notion of winding numbers. Okay, and then we moved on to surfaces. And in particular, sort of two-dimensional surfaces, and then we introduced two examples again of topological invariants, which are the notion of orientability and the Euler characteristic. So discussed orientability Euler characteristic. Showed how you could compute this, right? So how to compute this. And how to use it to classify two surfaces up to sort of homeomorphisms. Okay. And in particular, it's like if you had a two surface which was triangulated, it's like we discussed how to actually compute. We discussed algorithms for computing whether the surface is R interval and what its Euler characteristic was. Okay, all right. So those are sort of some sort of basic precursors, and then the next thing we did was to talk about complexes, in particular simplicial complexes. So we looked at complexes, in particular sort of geometric simplicial complexes, which are of course sort of a fundamental tool. It's like one uses in practice, right? And then abstract simplicial complexes. We discussed how that every abstract simplicial complex has a geometric realization, right? This is what is referred to as the geometric realization theorem. Okay, and in particular, we showed sort of a very systematic way to construct abstract simplicial complexes from sets of convex sets, right? So we discussed sort of convex set systems. And in particular, it's like we sort of looked at the intersections, it's like between convex sets and sort of in higher intersections, if you will. And that then it's like gave you some sort of notion of abstract simplicial complex through the notion of a nerve of a convex set system. So this notion of a nerve then sort of leads to one of the important examples of simplicial complexes, it's like which people study, which is the idea of the check complex, right? So this notion of the nerve, when applied to sort of balls of radius r, sort of centered about sort of a point cloud of data, right, leads to the check complex. Okay, and then the problem is that in practice, it's like the check complex is difficult to compute because you have to worry about, it's like the, intersections of multiple balls. It's like which can be, expensive to test, and so this is sort of, expensive to compute. So what one does instead is to just check that, you know, pairwise intersections arise. It's like, and then if basically if you're trying to construct a high dimensional abstract simplex, as long as all the edges, it's like, are there, which more or less means that as long as all the pairwise intersections, it's like, are there, then you put it into a new complex, which is not the check complex, but what's called the Vietoris-Rips complex. Okay, so if one just checks sort of pairwise intersections, instead of all possible intersections, right, one gets the Vietoris-Rips complex, which is easier to compute. But then there's this nice property that there's a sense in which the check complex and Vietoris-Rips complexes for different values of R are related to each other. Okay, so it turns out that the Vietoris-Rips complex, right, of radius R is contained in the check complex of radius square root 2 times R. Okay, and this is, and a check complex of a particular radius is always contained in the Vietoris-Rips complex of the same radius, because the condition for checking that some simplex is in there, it's like, is weaker, basically, strictly weaker, right? Well, not strictly weaker, because if you're in low dimensions, it's the same. Okay, but it is weaker. Okay, so there's this sort of nice nesting, it's like, if you will, it's like between the Vietoris-Rips complexes and the checks complexes. So in a sense, you don't really lose much, it's like, by working with the easier to compute Vietoris-Rips complex instead. Okay, so the problem, if you will, with both the check and the Vietoris-Rips complex is that now imagine your point cloud data, it's like, it's like it's in some sort of containing space, it's like, which is a particular dimension. You can still end up in a situation where, you know, it's like when you compute this check and Vietoris-Rips complex, the dimension, it's like, of the simplices you end up getting is not bounded by the dimension of the space the point cloud data is coming from, but rather by the number of points there are, right? So, basically, if you have n+1 points, then the largest simplex you will end up getting, it's like in the checks and Vietoris-Rips complex, is n. Okay, so that's not really, you know, what you want. It's like, and that sort of leads to the question: can you construct complexes which, you know, it's like, again, you have simplices or abstract simplices, but whose dimension is bounded from above, right, by the dimension of the space the data is coming from. Okay, so all right, so let's say a little bit about that, right? So we wanted to study ways of constructing complexes such that the top dimension top dimensional simplices, right, are bounded by the dimension of the containing space, right? Okay, so this led to a discussion of sort of Voronoi sort of cells and Delaunay triangulations. And sort of Delaunay complexes, right? So the problem, if you will, with Delaunay complexes is that you have this property that the simplices which you get, it's like from there, it's like bounded in dimension by the dimension of the space you're working in, which is good, but there's no notion of a sort of length parameter, which you had in the Czech and the Vietoris-Rips complex. So that leads to the idea of the alpha complexes, which are sort of a combination of the Delaunay complexes with the Czech complexes. So essentially the idea is that you look at the Delaunay cells, it's like which are, it's like the convex sets, it's like which you look at the nerve of, right? And then you sort of just intersect it's like those Delaunay cells, it's like with balls of the appropriate radius. So that gives you now a new convex set system, right? Which has the dual property that there's this grading in terms of the length parameter, as well as a limit on the maximum dimension simplices you have. It's like based on the containing embedding space. Okay. So so then by considering the sort of convex set system, right, consisting of Delaunay cells intersected with balls radius r, right, we get the alpha complexes, which have a length parameter and the dimension of the simplices are bounded by the dimension of the containing space. And that's basically what one should consider using primarily. Okay, so that sort of gives you a way of, so in particular the alpha point complexes give you a way of taking point cloud data, it's like, and then constructing it's like a complex, which is sort of a generalization of some sort of triangulation. And then on this complex, we want to start talking about how you compute topological invariants on that. And that's what leads to this discussion we had, it's like in the course about homology and things along those lines. So then we discussed sort of some topological invariants. On simplicial complexes. Okay. And okay, so the reason I should also probably mention is that there was this important nerve theorem, which basically says that the abstract simplicial complex you get, from looking at intersections of convex sets is encodes in essence the same topology, right, in an appropriate class, okay, as as the union, it's like of those convex sets, right? So this is called the nerve theorem, and it more or less says that if you're if you're interested in trying to compute, it's like you know, certain topological invariants, it's like of, it's like the actual domain, it suffices to compute those topological invariants for the abstract simplicial complex you get from the nerve, okay? And it's with the caveat that this is not with respect to the notion of equivalence, which comes from homeomorphisms, but sort of a weaker notion of equivalence, right? So in some sense, it doesn't capture as much information, but that's still okay. Okay. Anyway, so we wanted to discuss some. So we discussed some notion of topological invariance. It's like on these simplicial complexes, in particular, sort of homology, right? Which sort of intuitively, right, is related to the number of holes of a particular dimension. So it counts the number of holes, it's like of a particular dimension, it's like on the complex. Okay, and the way this is encoded is it has to do with looking at the boundary operator, and in particular, it looks at a hole is basically something whose boundary vanishes, right? But it's not the boundary of some higher dimensional thing, right? So so that's what one means by a hole here, okay? And all right, so that leads to this notion of homology. And then we had discussed at some point in time this idea of taking spaces and contracting them. It's like 2 points, and for the purposes of homology, homology can't distinguish between it's something which is contractible and a point. Okay, so and so it's natural. Because a point is so simple, it's natural to want that the homology, it's like of a point, it's like all things which are contractible, right, is somehow trivial. But the lowest homology group, it's like of the point is not trivial. So that leads to the idea of reduced homology. So we introduced sort of reduced homology. So that the reduced homology of a contractible space is trivial. Okay. All right. And if you recall, that involves sort of introducing an additional map. It's like which which more or less counts the number of connected components. Okay, all right. Anyway, okay, so the augmentation map. Okay. And then there was also the idea of relative homology, where you sort of you have a subcomplex. It's like alpha simplicial complex, and you sort of pretend that some complex is it's like you ignore things which are, you ignore chains as like which are related to each other or who differ from each other just by things which are in that subcomplex. So this is the notion of relative homology. And then, so relative homology, it's like is relevant. It's like when, again, it's like you're trying to consider the some of the exact sequences which show up, it's like with pairs of spaces. Okay. So anyway, so I'll go back to this. So we showed how to compute homology using matrix reduction of the sort of the matrix representation of the boundary operator, the boundary matrix. And the Smith normal form. Okay. Okay. And then we also talked about the excision theorem for relative homology. Right. So there's this excision theorem. And then sort of in terms of some general tools, it's like for studying or computing homology, we talked about how exact sequences show up. So discussed how exact sequences are an important tool. For computing homology. And in particular, this leads to the zigzag. This leads to the zigzag lemma, which you prove it's like through some sort of careful diagram chase to show that the obvious candidate sort of for the connecting homomorphism is actually well defined. Okay, and then one particular application of this is the important application of this is the Majorez theorem. And the Majorez theorem is important because it allows you to, it's like have a tool for essentially computing the topology, sort of the homology. It's like of a more complicated space in terms of simpler spaces. So in particular, it expresses the homology of the union of two spaces, A union B, in terms of the homology of A, B, and its intersections. A intersect B. Okay, and of course it's like once you've done that, you could imagine doing this repeatedly. It's like, and this gives you a way of hierarchically decomposing a complex object into sort of simpler objects where either you happen to know the homology of that simpler object or it's easy to compute. Okay, so it gives you some sort of divide and conquer strategy. It's like for computing homology of complicated systems. Okay, so all of this is like in the context of homology for a single given simplicial complex. But of course, when we were discussing, it's like these various ways of constructing complexes, in particular the check complex, the Varataris-Rips complex, and the alpha complexes, there was this notion of a length parameter, right? And so, so this length parameter leads to what is called a filtration of complexes. So these are complexes which are nested in each other. So because as you increase R, it's like you only monotonically adding simplices. It's like to these various complexes, you're not really taking anything away. And so it's very natural to ask, well, it's like, how do the homology groups, it's like of each of these sort of simplicial complexes in the sequence relate to each other, and whether homology generators in one, it's like persist, are still there, it's like in a later part of the filtration, or whether they get created or they get destroyed. Okay, so this leads to this notion of persistent homology. So we have sort of a filtration, right, which is a nested sequence of complexes, and we want to know, and because they're nested, there's an inclusion map. and this is endowed with inclusion maps. So we can ask if a homology class in one complex sort of still exists in the sort of larger sort of containing complex. Okay, and in addition to whether it exists, it also sort of leads to related questions, which is when it's created and when it's destroyed, as well as it was created or destroyed. Okay, and how long it lives, which is this notion of persistence. Which is persistence. Okay. All right. So in particular, it's like we discuss how to compute this efficiently, sort of in a simple way. So we can compute this using a variant of the matrix reduction algorithm we had, using sort of matrix reduction on a boundary matrix that encodes all the boundary operators of all dimensions. Okay, but it still doesn't, at least, it's like on the surface, address this issue, the fact that you have this filtration, right? But because this filtration, has a sort of a final complex, it's like which contains everything else, it turns out that you just really have to consider the boundary operator on that final thing. But in order to respect the fact that you have this filtration, you would want to write that boundary operator in a way where the simplices are ordered in a way which reflects the filtration. Okay, so it encodes the boundary operators in all dimensions, and the simplices, right, are ordered compatibly with the filtration. Okay, which is just a way of saying that if you have a filtration, if you have one of these simplices, if you have one of these sort of subcomplexes in the filtration, right, then the simplices that's contained in that are all sort of, corresponding to the first block of simplices in this ordering, right? And so you can sort of imagine just sort of throwing the subsequent blocks away. And so in any case, it's like if you write down this sort of boundary matrix in a way which, it's like encodes all the operators in all the dimensions, as well as ordering the simplices in this way, it's like which in some sense reflects the filtration ordering, then you can do all these operations at once, and then it's like there's a way to interpret the result in terms of this notion of persistence, in particular when a homology generator is created and when it dies. Okay, so so those are sort of some of the main ideas. It's like sort of in the last week we also talked about the idea of Morse functions, and unfortunately we didn't have time to finish talking about that. But hopefully at least it's like you get sort of the main computational tool, it's like which is used in applying computational topology. which is the persistent homology part, right? And as a recap, the reason why it's like one studies persistence is because, of course, in practice, the noise it's like which you're trying to, it's like extract topological information from. The data you're trying to extract topological information from is noisy, and so it's possible that if you don't, it's like if you just directly apply topological techniques to it, it's like you're really sort of measuring the topological features which are a consequence of the noise as opposed to sort of the underlying properties of the space which the data is sampled from. Okay, so the hope, if you will, is that if you are able to distinguish between topological features, in particular homology classes, which persist for a long time, versus those which just sort of come on, it's like at, for a short instance and they disappear. The hope is that the ones which persist for a long time are really the ones which reflect the underlying topology of the space the data is being sampled from. Whereas the ones which are, persist for a very short period of time, one tends to assume it's related to the noise. Okay, so let me just stop here. It's like, and thank you for taking this class. And I'll be happy to answer any questions you have online. Right. Thanks.